All right, so just a reminder, what is going on this week that's a big deal to you? Benchmark, right. So right now, spoke to other teacher, it has to be on Thursday. I know last week I was starting to promise you guys that we could do the lab or something more, a little bit more interesting than just sitting in our desk taking a test. But unfortunately, the test is going to be Thursday. So we're going to start our review tomorrow, okay? And that'll, so today we're going to do a little bit of practice, none of that, a little bit of practice, and then I'm going to give you one last set of notes, which just explains kind of how the graphs work. That'll be useful to you. And then we're kind of done until after the benchmark. So what that means is no lab this week. We'll do the lab on Monday. It'll be the way you come back from a 3-day weekend. So, so just be ready for that. If you're going to be missing, you got to get your pre-lab done over the weekend. All right. So a reminder of what happened last week. Okay, so I'll just kind of do a quick run through, but if you missed last week, you should probably watch the video from last week, okay? We started talking about what thermochemistry was. We talked about how we have the joule. Q is one of our new variables. We didn't do much with work. We didn't do much with the W, but we did talk about the Q. Okay, and that's going to be your energy and motion. So the whole idea about a lot of these calculations right now is heat flowing into something and heat flowing out of something, so that we got our positive and negative values, okay? We talked about the calorie, how this is not like our food calorie, right? That's a kilocalorie, but it's defining our specific heat capacity of water, all right? We also talked about specific heat capacities of different things relating to a pool. And so in the middle of summer in San Antonio, the water remains pretty cool and the concrete you guys can't walk on, right? So low specific heat versus high specific heat. Big question today, everybody keeps asking me, is the P necessary? No, I do it out of habit from when I used to do it. So you do not need to write the little P next to it, okay? Next thing is we learned this little formula right here. Okay, and so what we're dealing with is we got some mass, we have specific heat capacity, which is specific to every single element out there and every kind of stuff out there, I guess you could say. And then your change in temperature is going to be your final minus initial. Today I'm going to provide you with one where you are solving for temperature final, so kind of think ahead about how that algebra is going to work, okay? All right. The lab you're going to be ready for on Monday is going to be a calorimetry lab where you use their fancy styrofoam cups with a lid, right? And we're going to measure the temperatures, which will define for us whether energy was flowing in or out of a certain thing that we put into the cup. I don't know if I made a big deal about it to y'all, but if I did not, can you please add like a nice special box or stars around that last little sentence? Because we're going to talk about the graph today, and you'll kind of see it, but what I need you guys to realize is Q is delta H, all right? So H itself is called enthalpy. Don't worry too much about that right now. What I need you to know is when you put that delta in front of it, this is now equal to Q, which that should make sense to you, because that's what we talked about on Friday, which is just the heat flowing into and out of your system. So positive versus negative. So this is telling you the same exact thing right here. Okay? So today when we look at our graphs, we're going to stress endo and exothermic and what do those look like in terms of where the energy diagrams are. You guys all good with the old stuff? We're all ready to move on?
Sure.
As good as we can be. Positive vibes only. All right. Okay. So in this class, did we end up going over this problem?
Yeah.
Or did we just start it?
No,
we went over it? Okay. All right, so I'm just going to review it because not everybody was here. So listen. Shh. Okay. So we have Q equals MCAT. We expanded it out to add in the temperature final minus initial, and we can rearrange it to solve for your specific heat. The first problems on this page are all asking you to solve for specific heat. So you're going to be using that bottom version right there, okay? When we did our problem, we found out that we had heat. What was special about this word applied to? What was special about that? Made it a positive value, all right? So make sure you are paying attention to verbs. Verbs, yes? Action words. All right, good. All right, so make sure you're paying attention to that. If it says it's being released, if it's saying absorbing, and anything like that, you want to pay attention to that, because that tells you whether this number starts off positive or negative. And usually you can look at your temperature change, and that'll give it away as well, right? So if temperature drops, energy was released, it was negative. If it gains, then you're going to have a positive value. All right, so once we got that, the other thing, what did we notice about our units for temperature? What do we not have to change them into? Right, we don't have to change them into Kelvin. You can leave them in Celsius, so good. And then you go ahead, and you guys went ahead and plugged this in. I did not realize this wasn't finished right here. Sorry.
Finish it, that's why.
Oh, you guys didn't finish it.
Yeah, we got up to that point.
Oh, good. Okay, so you end up typing in your energy is a positive 34,700, and we're dividing it by mass times that temperature change, which is 151. Please remember, you do not need to put all these little parentheses there. I do that because it's easier on the eyes. Just put parentheses around the outside and put a little multiplication symbol in between. Once you do that, you end up getting 0.65. And let's look at how we do our units, because on the back of this page, number 6, they trick you on your units, and they show you a different unit. But it doesn't change anything. It comes from the calculation itself. So what is energy measured in? What was the energy measured in? Joules. So we're going to say joules, and then we're going to put the little fraction in, then we're going to say, what was mass measured in on this? Grams. And your temperature was measured in degrees Celsius. And that's how you're going to get your units. Please work on your units today when you're calculating. So, so that was that problem. See a few more people copying. We're all good? Okay. So what I want you guys to do is for the next 15 minutes, I'll leave this up here. Oopsie. I'm going to have you guys work the problems. What I want us to do is on the back you have a little gap. I do want everyone to, you don't have to write down the whole problem, but if you can write down the details from this question. This is one where you're solving for a final temperature, okay? And this right here is the answer. This approximately, there it is. Approximately 4 degrees Celsius right here. It's like 4.6 is the answer. So you just have to write down the details. You don't have to write down the entire problem word for word. But I will go ahead and leave this up, and you guys can work on these, okay? So I'm going to put this right here, and I'm going to move this guy down. You have all the answers you need. Okay? So go ahead and work on this for 15 minutes. All right, so on your blank page in your packet, basically this whole first slide that I'm going to draw all over, I only want you to use the top half of the page for. But you can use the whole top half of the page. And then I'm going to show you 2 other little graphs. We're going to squeeze those in at the bottom half of that page. Okay? Are we all clear on that? Yes, Miss Paula. All right. So the top half of the page, we can go ahead and title it. We can just say these are graphs in thermo if you want. Okay? Okay, and that first graph that I'm going to have you make needs to have a long x-axis. Okay? We're going to kind of write a couple things along the graph. We'll write a couple things below the graph, so don't just, keep that in mind as you guys are using a certain space. Hold on a second. Okay. All right, so my x-axis, we're going to go ahead and label as heat. So what this means, what variable do we use for heat? Q, good. And then today I taught you delta H is the same thing, okay? So what this means is I am obtaining heat. So as I get bigger on the x-axis, that means that I'm absorbing more and more heat, okay? So your y-axis is going to be temperature. As I absorb heat, what happens to temperature usually? Goes up, yeah. So we're going to kind of watch that happen on our graph, okay? So the way I want you to make this graph is I want you to have I'm really interested if I have like a line thing. Nope, I don't. Okay, I'm gonna give up on that dream. Hold on. All right, there you go. All right, so I want you to make like kind of a steep slope like that. Okay, and then you're gonna level out for a flat line, not too long, but just a little bit. Okay, and then you're gonna do another little slope, not to the top yet. And then we're gonna have a longer flat line. And then we're gonna have one more angle over here. Okay? So you just have a graph that kind of looks like this. Okay? What this graph is called is this is your phase. Actually, sorry, I'll write it above it. This is your phase diagram for water. Okay? Your phase diagram for water. So when I say phase, what is that talking about? States of matter. So give me the 3 states of matter that we usually talk about. Solid, liquid, gas. Okay, so that's all that we're talking about. So what this graph is showing is that as I absorb some heat, okay, I'm going to be changing my states of matter. So if I have absorbed a lot of energy, what is this side of the graph probably representing? Gas, exactly. So put a little G there. And it is specifically the diagonal part, okay? All right, in the middle, we're gonna put liquid, and down here, we're gonna say solid, okay? Since this is very specific to water, okay, if I were to tell you that this is exactly when it turns into a solid, okay? What is a solid water called, by the way? Ice, right? What temperature is that?
0 Celsius.
Good, perfect. 0 degrees Celsius, all right? And if this part right here was where water was turning into gas vapor, water vapor. That's where it was, what temperature is that at? 100 degrees Celsius. Those are 2 numbers you do have to have memorized, y'all. Okay, so that's the boiling point of water, right? Freezing point of water, boiling point of water. All right, so what do you guys think this is right here? These 2 lines. They're the transition to each, good. Okay. So let's go, since we know what the transitions are called, let's go ahead and call it. So what is it if I'm going from a liquid to a gas? Mm-hmm. So it's the process of evaporation. And if we were going from a gas down to a liquid, what would that one be called? Condensation. Good. Okay. Let's label this one down here. So if I'm going from a solid to a liquid, let's see if you guys get it. All day, everybody's like gone blank on me. No. What? There is no shun in this one.
Melting.
Thank you. I swear, that's been like the hard one for everyone. All right, this is melting. I think everybody wants a shun at the end of it. It is meltshin. Meltshin is happening, you guys. All right, and then what's happening if we're going from liquid to solid? Freezing. And actually, the science word you should be using is fusion, you guys. This one does end in a shun. All right, but it is freezing. Fusion is more, yeah, because you guys are going to learn about your heats of fusion and heats of vaporization, okay? So, these 2 parts right here, I also want you to label with this, okay? These are parts of equilibrium. So what that means is it means both states of matter are actually existing for that duration of time. All right, so this whole heat being absorbed, you can kind of imagine this almost like a time part down there. So if right here we have, right here we have liquid, right? So what it's going to do after it's a liquid, okay, is it's going to keep absorbing heat, Is it changing temperature as it's absorbing heat? No, that's what the flat line is showing. So it's sitting there at 100 degrees Celsius, sitting there absorbing as much heat as possible, but it's still liquid and gas at the same time. And then it's not until this part, after it's absorbed this much heat, that it bumps up another phase. And that's what I want you guys to start grasping for thermo, is that just because temperature changes, it doesn't automatically mean, just because temperature changes doesn't mean everything's absorbing the same amount of energy, all right? It's a little more complicated than that. I also want you, so the thing that'll help you visualize this one's kind of tough for everybody to visualize, but I want you to visualize this one. Have you ever had a pot of boiling water on the stove and you put the lid on it? Like a clear lid. So what do you see? You see vapor coming out, but what happens once it hits the top? It condenses back down, right? So you have this little idea where you have a lot of it coming out of the liquid and going back into the liquid. And if you think about that rate being equal, that's this part right here, okay? That's kind of like what equilibrium is. Not completely, but it's the best visualization that I could come up with, okay? Right, so eventually it absorbs so much energy that now it's just all coming out of the liquid and going into gas phase, okay? So it's kind of the way to think of it. All right, so one more thing we got to add to this nice little graph, and we're just going to write it down below, and that is, as I proceed in this direction on the graph, so as I'm going from solid all the way up to the gas, is that an endothermic reaction or an exothermic reaction? What's your first instinct tell you? Usually the answer is exo, and that's because what do we think of when we hear the word exo? Hot or cold? We think hot. We're like, energy is being released, there's hot. Yeah, okay, but what's happening this whole time you're going up? Are you absorbing energy or releasing energy? Look at your graph one more time. I'm gaining heat, right? This is showing that I'm absorbing heat this whole way. So this is exothermic. Oh, I just made that big deal about it, and then I messed it up. Sorry. This is endothermic. There you go. Okay. As I proceed the other way, so if I'm going from gas down to a solid, now what do I know that is? Exothermic. I'm releasing energy. Now that's, oh my God, there's a spider on me.
Told you it was going to be 3 times the charm.
Sorry, you.
All right, so this one is exothermic, my bad. All right, so the way that you can kind of think of this, because what we're going to get to soon, besides phase diagrams, is when you are breaking bonds versus forming bonds. When you are breaking bonds, that's going to be an endothermic reaction. So we're increasing something called entropy, which is disorder. And then as we are becoming more organized or forming bonds, those are going to be exothermic reactions. And the way I like to think of it is nobody wants to stand next to you if you're letting out all this energy and you're like flailing your arms, right? So, I'm sorry. You have to let all the energy out so that you're not flailing your arms and somebody will want to stand next to you, right? So you gotta release energy to wiggle in closer together, okay? That's kind of the way I think of it. All right, the last part. So this is now at the bottom half of your paper. I want you to give yourself 2 small graphs. There's not too much to say about these, but these are important. These 2 graphs you should have seen in biology, okay? One looks like this. The other one looks like that. Yeah, woo! All right. So, what goes on the x-axis of both of these is going to be, reaction, progress. All right, I'm just gonna say reaction progress, and I'm too lazy to write it on each one, so that's what the x-axis is. All right. Your y-axis. Who remembers what these what were these diagrams showing you? So yeah, so you guys learned about catalysts and enzymes, which were dealing with this part up here. What did catalysts and enzymes mess with? The activation. Yeah. All right. So if this is a measurement of energy, isn't that what the whole y-axis is? I'm just going to put AE. Okay. So your whole y-axis right here is talking about potential energy. all right? And so for chemistry, we're not just going to worry about, oh, let's put a catalyst in there and mess with our activation energy, lower it so that it goes faster. I don't want you to be thinking about that, okay? What I want you to think about is this part. This is thermo right here. Okay? If this represents your delta H's, which is also your Q value, what is this one right here? Is this a positive or a negative? The very first graph. Is this a positive or negative change? If I start up here and I end way down here, did I lose energy or gain energy? Lost. So is that positive or negative?
Negative.
Negative. This one over here, I started down here. I ended way up here. What is that?
Positive.
Positive. Okay. So this first graph, is it endo or exothermic? Exo. Good. Perfect. All right. So you guys got it. Tomorrow we're going to review.